The topic of discussion in today's class is moving coordinate system. Now, during the review of elementary mechanics principle, Newtonian mechanics principle, you probably recall this picture. We have a frame which is fixed and which is given by x prime, y prime, z prime, and there is another frame which is given by this set of axes x, y, z. Now, a particle which is moving in space, the position vector measured with respect to this frame is r prime and with respect to this frame is r. Now, if the location of this origin of this particular frame is capital R with respect to this frame, then we can write R plus R is equal to R dashed. This is just from vector addition. Now, if this is the case, then R double dot is equal to capital double dot equal to small r prime double dot. Now, if we multiply this with the mass of this object m in both sides, so this is the acceleration which is measured with respect to this particular frame. So, let us say this frame is moving with respect to this frame, this is fixed and this is moving. So, we see that m r prime double dot is the force which is measured with respect to this primed frame inserted on this particular object. Now, if we similarly so this one gives this one will give a force which is measured, the force which is measured from this particular frame inside being working on this particular object. Okay. And of course, there is this additional term m r double dot. So, we see that, now forget about the arrows. Now, this primed frame or this particular frame, let us consider this to be fixed and this to be moving. And we have discussed that if this is moving with an uniform velocity, that means if r dot is equal to v equal to some constant, then we immediately see r double dot is equal to 0 and these two forces, measured forces, are equal. Okay. So, that means if this moving frame is moving with an uniform velocity, then it is called a inertial frame. But if the velocity is not constant, that means the acceleration, there is a non-zero accelerating term, that means this equation, in this equation all the terms survives and the force inserted on the object which is measured from, depending on whether we measured the force on this object with respect to a fixed frame or respect to a moving frame, the amount of force is changing, and this additional term is called a fictitious force, fictitious or pseudo force. It is not a real force, it is coming up only because this frame is moving with some non-uniform velocity. So, this fictitious or pseudo forces are what makes life really difficult when we are sitting and when we are trying to measure something with respect to a moving coordinate system. Now, in this chapter we will be discussing a special type of moving coordinate system, which are actually rotating coordinate systems. So, the situation is as follows. okay, I will just keep it there. So, let us say this is our fixed frame of reference and this is our moving frame of reference which share the origin common. So, the origin is common. Okay. So, if this is my x prime, y prime, z prime, then this is my x, y and z. So, and see here what we have discussed is a general motion. It could be a translation motion, it could be a rotation motion, but here the situation described is a pure rotational motion. The origin is common and let us assume that there is some axis along which this one frame is executing a rotational motion with respect to the fixed frame. So, this purple frame, this one is fixed. Okay. So, this 3 sets of axes, they are fixed in space and the other 3 sets of axes, they are rotating in space and the rotating with this, the origin remains a common point between these 2 frames and there is an axis of instantaneous rotation, let us call it n cap, and the rotation is taking place around this particular axis. So, this is the situation we are going to describe in today's class. Okay. So, this is a case which is case of rotation. Now, let us assume a situation where the rotation is with an uniform velocity. So, let us assume that the velocity is the rotational velocity which is described here is omega, which is some kind of a constant. Okay. So, let us see, let us assume omega equal to constant. I mean omega vector is constant, just a minute. So, this is my direction and the rotational velocity omega, which is the velocity of rotation of this rotation, is a constant. So, omega vector constant means not only the direction of the vector is constant, but also its magnitude is a constant of time. Is this equation, I mean, so my question is, does this uniform rotation still gives rise to a fictitious force? The answer is yes, because any rotation, even if it is a uniform rotation, it will definitely give rise to a fictitious force for the very simple reason. Let us assume a point moving on this circle with an uniform velocity omega. Okay. So, the direction of velocity, okay. So, probably we all know this, if the circle, if the point is moving on this particular frame in clockwise direction, then the direction of velocity is axis of this angular velocity omega is out of the plane, and if it is going in a clockwise direction, then the direction is inside the plane. Okay. So, I hope we are familiar with this notation. Now, if omega is constant in this case, think of it, the velocity, the corresponding linear velocity, if the radius vector is r, then they are related, the speed v and this omega is related by v equal to r omega. Okay. Fine. But the direction of v is changing continuously on this circular loop, right, is not it? So, although the magnitude of velocity remains fixed, the direction is constantly changing. So, we can say even if for omega equal to constant, v is not a constant, right. So, that is why even if there is an uniform rotation around a fixed axis with a uniform angular speed, does not mean that it is a inertial frame, inertial system. A rotational velocity will always give rise to a rotational motion will always give rise to a linear velocity which is not a constant with time. So, that means there is always a pseudo force acting on this. So, our job is to find out the pseudo force. Okay. Now, let us for a second forget about, for now let us forget about this constant omega it is not important, we will just do a derivation for a general omega. Let us assume that there is a vector which is okay. So, let us assume that there is a vector which is given by represented by G. So, let us say this is the vector, okay, some vector. So, okay, so it need not necessarily be starting from the origin, it could be anywhere. So, this is a general vector. Now, this vector will have components in both the frames. So, G will have, we can resolve the components of G in the fixed frame, that is the primed frame, or we can resolve the components of G in the rotating frame. Now, once we do that, and please remember whether although the frame is rotating does not matter, if we write the vector G, the vector G remains invariant whether we represent it in this frame or the other frame. So, we can write G to be equal to G1 prime I cap plus G2 prime j cap plus G3 prime k cap. So, sorry I cap prime, j cap prime and k cap prime. So, let us assume that for the fixed frame we have k, for example, k cap prime, I cap prime and j cap prime, and for the moving frame let us have I cap, j cap and k cap. Okay. So, now onwards whenever we will be referring to a moving coordinate system, we will be whenever we will be discussing a fixed coordinate system, if there is a fixed and a moving coordinate system, the fixed coordinate system will be denoted by prime and the moving coordinate system will be denoted by this non-primed numbers, non-primed indices. Okay. So, we just resolve the components. This is in the fixed frame and this is in the rotating frame. So, the equation what I have written here is nothing but equivalent of writing G fixed, which is the vector G in fixed frame, equal to G rot, the vector G in rotating coordinate system. Right. Now, if we want to take the time derivative of this vector, how are we going to do that? So, of course, we can just take time derivative of both sides of this. So, which will be given by dg dt. For left hand side we will have dg dt fixed, which will be given by time derivative of this one. Now, please now note I prime, j prime, k prime, these are unit vectors in the fixed frame, and because they are fixed in space, their time derivative is always 0. So, if we take the time derivative of this one, it will be simply dg1 prime dt I cap prime plus dg2 prime dt j cap prime plus dg3 prime dt k cap prime, right. And on this side, now this will be equal to dg dt rot, okay, because if we take the time derivative in rotating frame, it will also be the same time derivative, right. So, we can write this as I cap plus dg2 dt j cap plus dg3 dt k cap plus 3 additional terms, because I, j and k, they are also changing direction with time. So, we have g1 di cap dt plus g2 d j cap dt plus d3 g3 d k cap dt, right, and this is equal to d g dt rot. Okay. So, one side we have dg dt fixed, one side we have dg dt rot, which has to be equal, because irrespective of which frame we represent the vector, the vector itself and also their time derivative has to be equal. So, this two has to be equal, right. Now, if we examine this, the first term is, so if we now write dg dt rot separately, we see that dg dt rot is equal to, the first three terms is nothing but dg dt with respect to rotating frame, right. Look at the first three terms. It is the instantaneous representation of the vector, the time derivative of the instantaneous representation of the vector in the rotating frame. And for the other three terms, we have to see. Now, let us consider this for a moment. Let us say we have this some vector A, and this is an direction n, there is a vector A, let us say this angle is some fixed angle, let us call it phi, okay, and this is some vector A. Now, this vector is rotating around this particular fixed direction with maintaining this fixed angle. So, the situation is something like this. So, let us say I have a red pen in hand and I have a green pen in hand. So, let us say this red pen represents the fixed direction and the green pen represents the rotating vector around this particular direction, okay, and this angle is fixed. So, it is rotating something like this. Okay. So, the rotation is something like this. So, the angle is fixed and the direction of this vector is changing. Now, if the direction of this vector is changing with time, okay, so we have A here, and at a later time it moves to a position. Sorry, this picture is not very clear. I will try to draw a better picture. Right. So, whatever happens, this is n and this is A, the tip of the vector A will remain on this cone, right. So, in a later time it will go here. Now, this vector is not exactly a vector, but it is a vector which is A plus delta A. Delta A is this one, right. Now, what is delta A? Delta A, if you just a minute, right. Now, if this angle is your delta theta, then we can write delta A, the magnitude of delta A will be A times the magnitude of A times delta theta, right. And what is the direction of this delta A? The direction of delta A in the limiting case, try to realize this, it is a direction which is perpendicular to both n cap and A, right. Because, so in the limiting case, when A and A plus delta A, they are almost coinciding on each other. It is something similar to the construction we did for when we were determining the time derivative of the derivative of theta cap and r cap in plane polar coordinate system. So, in the same notation we can in the same line of thinking we can write delta A vector is equal to A times delta theta, sorry, this will be delta A will be equal to so right, it will be the magnitude will be A delta theta and the direction will be n cross A cap, right. Now, n cross A cap being a unit vector along A direction. So, we can absorb this here and we can rewrite it as n cap delta theta cross A, right. So, change in delta A, the magnitude of this will be, as I discussed already, magnitude will be A times delta theta and the direction will be perpendicular to both A and delta A. So, we can write delta A vector is equal to n cap cross A times delta theta, or actually we can write delta theta outside also, n cap cross A times delta theta. Now, if we try to take the time derivative of dA, I mean time derivative of A, then we have to divide this thing by delta t on both sides, this whole thing by delta t, and we have to take limit when delta t goes to 0. Now, if we do that, we immediately see your dA dt is nothing but n cross A times theta dot. Okay. So, this theta dot is this angle, the angular change of this vector, and theta dot is nothing but omega, if omega is the instantaneous angular velocity of rotation. Okay. So, what we can do is we can substitute this with omega, and please note that omega vector is nothing but omega n cap, right. So, because n cap defines the direction of omega, this is the direction of this rotation vector, and omega, which is equal to theta dot, is the instantaneous speed of rotation, right. So, we can write omega vector as omega cross n cap. So, with this we can simply write dA dt equal to omega cross A. So, this is a very important relation. So, the result says for pure rotational motion around a fixed axis, the time derivative can be represented by omega cross A, right. Now, we use this result for these three time derivative. Okay. So, di dt will be omega cross I, dj dt will be omega cross j, and dk dt will be omega cross k. Now, if we employ that here, so I am removing this part, we do not need that anymore, whatever we have had to prove, we proved. So, you see this first term of dg dt rot is dg dt measured at the with respect to the instantaneous x y z axis, and the second term will be g1 remains g1 into omega cross I cap plus g2 into omega cross j cap plus g3 into omega cross k cap. Okay. So, if we write it little more, we rearrange it, we take omega cross out from each of this and write omega cross g1 I cap plus g2 j cap plus g3 k cap, then what we get is this dg dt rot plus omega cross g, right. And now for the left hand side, dg dt, the time derivative with respect to rotating frame, is equal to time derivative with respect to fixed frame, and that is equal to equivalent of writing. Okay, so this one, instead of taking with respect to rotating frame, we can take it with respect to fixed frame. So, instead of dg dt rot, we can write dg dt fixed. Please understand that this is equivalent of writing dg dt fixed. The entire bracket, when we use an entire bracket, that means that the time derivative is executed with respect to the fixed frame, and when we write a subscript type, that means the time derivative measured with respect to the instantaneous position of the value, fixed frame. Now, for fixed frame, the instantaneous position and the overall time derivative is the same, because it is a fixed frame. For rotating frame, it will be, there is one part which is the instantaneous time derivative, and there is a term which is omega cross g, right. So, we finally get the very important relation what we are looking for, right, which is, please note that it is derived for a general vector g. We have not assumed any specific properties or any specific characters of g. So, that means it will be true for any arbitrary vector in the 3-dimensional space. Now, if we understand this, then we can essentially, we can operate this particular, we can have this type of operation for any vector in the 3-dimensional space. So, we can replace this, we can get rid of this g, and we can create an operator which is d dt fixed equal to d dt dot equal to omega cross plus omega cross. So, what it means is the time derivative which is measured, the time derivative with respect to a fixed frame of reference is equivalent of time derivative measured with respect to a rotating frame of reference plus omega cross, omega being the instantaneous velocity of rotation cross that particular vector. Now, if we operate this on the standard position vector r, what do we get? We get dr dt is equal to dr dt fixed, we are just writing f for it, equal to dr dt rot. Okay, so, let us plus omega cross a or omega cross r. Okay. So, what is this dr dt fixed means? That means, if we are measuring a velocity, so dr dt is velocity. So, if the velocity is measured with respect to a fixed frame, let us call it v0, okay. And so that will be a combination of the velocity, the same velocity. Please understand the vector g or r or whatever we put in here, this vector is frame independent. The vector remains a vector is a quantity. Okay. So, vector does not matter if we measure it in with respect to this frame or that frame, the vector represents the same quantity. So, the velocity which is measured with respect to a fixed or inertial frame, if that is v0, then the same velocity measured with a non-inertial frame which shares the same origin as with the inertial frame will be v, where v is the velocity measured in that non-inertial frame plus omega cross r. Okay. So, now you bring it in terms of, so for example, let us take an example. Okay. Our earth is a rotating coordinate system. We take it as fixed, but it is not, strictly speaking, it is not a fixed frame. So, when we are measuring some velocity on earth, so in principle, as our frame of reference is earth, and now if we measure the velocity from outer space, which we go to some spaceship which is fixed in outer space. So, that is the same velocity if we measure from outer space will be v0, the velocity we are measuring from earth is v. So, we will see that this is related by v0 equal to v plus omega cross r. So, in that case omega will be the angular velocity of earth's rotation. Okay. So, in next class we will start from this point and we will see how this how this will lead to any other fictitious forces. Thank you.